Welcome to this presentation on Monolithic Microwave Integrated Circuits, or MMICs. This video is presented by Professor Gottapu Sasibhushan Rao. As shown in the slide, MMIC technology integrates microwave components on a compact chip and makes extensive use of structures such as microstrip and transmission lines for high-frequency signal processing. In this presentation, we will discuss the basic concepts, materials, fabrication process, and important MMIC device structures. This slide presents the contents of the MMIC topic. We begin with the basic definition of MMIC and important fabrication terminology. Then, we compare MMIC with conventional ICs and hybrid microwave integrated circuits, followed by its advantages and disadvantages. Next, we discuss the MMIC fabrication process, including GaAs MESFET fabrication using epitaxy and mesa isolation, and MOSFET fabrication using oxidation and diffusion in silicon technology. Finally, we compare the operating principles of MESFET and MOSFET. An MMIC, or Monolithic Microwave Integrated Circuit, is a microwave circuit in which the active devices, passive components, and interconnections are fabricated on a single semiconductor substrate using planar fabrication techniques. A common substrate is semi-insulating gallium arsenide, or GaAs. Because the entire circuit is formed on one chip, MMICs are very compact, have low interconnection parasitics, and are well suited for RF, microwave, and millimeter wave applications. This slide shows the typical components integrated in an MMIC. The active devices include MESFETs, HEMTs, and HPTs, which provide amplification and switching functions. Passive components such as resistors, MIM capacitors, spiral inductors, and transmission lines are also fabricated on the same chip. The components are connected using metal interconnections, air bridges, and wire holes, resulting in a compact microwave circuit with very short interconnections. This slide introduces the important terminology used in MMIC fabrication. Epitaxy means growing a fresh crystalline semiconductor layer, while lithography transfers the required circuit pattern onto the wafer using a mask. Etching removes unwanted material, and doping or implantation forms the required active regions. Metal deposition creates contacts and interconnections, while annealing is a heat treatment step used to improve material and contact properties. A Schottky barrier is the metal semiconductor junction used for gate control in devices such as MESFETs, and passivation protects the surface. The slide also shows air bridges and vias, which provide microwave interconnections while helping to reduce unwanted parasitic effects. This slide compares conventional ICs, MMICs, and hybrid microwave integrated circuits. Conventional ICs mainly use lump circuit behavior, where voltage and current relations are analyzed using circuit laws. In an MMIC, the active and passive microwave components are integrated on a single semiconductor chip, and at high frequencies distributed effects, transmission line behavior, S parameters, and electromagnetic analysis become important. In a hybrid mic, separately fabricated active devices are mounted and interconnected with passive components and transmission lines on a common substrate. Thus, hybrid mics combine distributed microwave behavior with lumped components, while offering greater flexibility than a fully monolithic MMIC. This slide summarizes the advantages and disadvantages of MMICs. The major advantages are compact size, low parasitic effects, high reliability, good repeatability, and suitability for mass production. Since the interconnections are very short, MMICs provide good performance at microwave frequencies. However, they also have limitations such as high initial fabrication cost, difficulty in repair or modification, limitations in realizing large passive components, restricted power handling in some technologies, and thermal management challenges. This slide shows the main material groups used in MMIC fabrication. The substrate, such as GaAs or InP, provides mechanical support, supports epitaxial growth, gives electrical isolation, and also influences RF performance and heat dissipation. Conductors, such as gold or aluminium, are used for ohmic contacts, gate metallization, interconnections, transmission lines, and bond pads. Dielectric materials, such as silicon nitride and silicon dioxide, are used for passivation, insulation, gate dielectric structures, and capacitors. Together, these materials determine the electrical, microwave, and thermal performance of the MMIC. This slide shows the overall MMIC fabrication flow. The process starts with the selection of a semi-insulating GaAs substrate, followed by epitaxial growth of the active semiconductor layer. The required device regions are then defined by photolithography and MESA isolation. Next, ohmic contacts are formed for the source and drain, followed by the Schottky gate. After that, metallization is carried out for interconnections and passive components. Finally, the circuit is protected by passivation, followed by formation of air bridges, bonding pads or vias, and then testing, dicing, and packaging. This slide explains the fabrication and operation of a GaAs MESFET. Fabrication begins with a semi-insulating GaAs substrate, followed by growth of an N-type epitaxial active layer. The device region is then defined by photolithography and MESA isolation. Source and drain ohmic contacts are formed, and a Schottky gate is placed between them, followed by metallization and passivation. As shown in the upper figures, with no negative gate bias, the channel remains open and current flows from source to drain. When a negative gate voltage is applied, the depletion region under the Schottky gate widens, narrowing the N-type channel and reducing the drain current. The lower figure shows the final MESFET structure, with the semi-insulating GaAs substrate providing isolation and the Schottky gate controlling the channel. This slide explains the fabrication and operation of an N-channel MOSFET in silicon technology. The process starts with a P-type silicon substrate. Heavily doped N+ source and drain regions are then formed by diffusion or implantation. A thin silicon dioxide gate oxide is grown, followed by deposition of the gate electrode, metallization, and passivation. As shown in the upper left figure, when no inversion channel exists between source and drain, so the device is off. When a positive gate voltage is applied, the electric field through the silicon dioxide attracts electrons to the surface and forms an N-type inversion channel, as shown in the upper right and lower figures. This induced channel connects the source and drain, allowing the drain current to flow. This final slide compares the MESFET and MOSFET. In a MESFET, the gate forms a metal semiconductor Schottky junction, and the channel already exists. The gate controls the drain current by changing the depletion region within this channel. In contrast, a MOSFET uses a metal or oxide semiconductor insulated gate, and the conducting channel is created by inversion when the proper gate voltage is applied. As summarized in the table, the MESFET has no oxide gate insulation and may have a small gate leakage current, whereas the MOSFET has an oxide-insulated gate with ideally negligible gate current. The main difference is therefore, MESFET controls an existing channel by depletion, while MOSFET creates and controls an induced channel through the oxide electric field.